All right, so we are going to start talking about chapter 6. I'm going to create a couple of videos I'm going to post on Blackboard for you guys, going through the notes that are also posted in Blackboard so you can kind of follow along with what's going on here. I am going to go a little bit faster than I would normally go in class because you have the luxury of being able to pause this, rewind, and go back and review it. If you have questions, I'll be available in Collaborate in Blackboard. I'll send you all an invitation for that on Friday, so that way we can talk about some of the things that we're going over in this chapter. So let's begin. So we're going to talk about rational expressions in this chapter. This is about simplifying rational expressions, multiplying rational expressions, dividing rational expressions. Everything is about rational expressions. So if you remember the last time we talked about, rational functions, one of the things that we talked about was that the denominator cannot be equal to 0. And we talked about that in a pretty basic way back when we originally talked about this idea. But now we're going to be able to ramp up these polynomials in the numerator and the denominator and see what we can do with those. So if you read this question, it says, give the domain of each rational function using set builder notation and interval notation. I'm just going to focus on the set builder notation for now, since this is pretty new for us. We've done interval notation quite a bit, so I'm not going to focus too much with that. But one of the biggest things that we need to understand when it comes to finding the domain is that there's something that makes this function undefined. Whenever you have a rational expression, if the denominator is 0, that's going to cause that entire function to be undefined. So what we do is we set the denominator to not be 0. So we need to figure out what's going to make this thing not be 0. So the first thing that we want to do is we want to factor the denominator as much as we can. We'll see that this is a quadratic trinomial. So this will factor to be x minus 3 and x plus 2 is not equal to 0. So we're going to get x cannot be equal to positive 3 and x cannot be equal to negative 2 using the shortcuts that I showed you back in chapter 5. All right, so these are the two values that x cannot be equal to, because if they're equal to 3 or they're equal to negative 2, that's going to make the denominator 0, and we don't want that because then that would be an undefined function. So set builder notation is created this way. So first of all, it needs to be a set. So we use the curly brackets just like we did before, and we start with an x, and then we put a bar here, and this bar represents such that. So this is x such that x cannot be equal to the two values that we found by factoring. So 3 and negative 2. And that's it for this first one, okay? And then for the part B, for example, 1, is the same thing is going to happen, is we're going to set the denominator so that it's not equal to 0, which is already the case. So there's no restriction on this function. The thing that you need to be mindful of and start to be skeptical is when you have variables in the denominator. Since there are no variables in the denominator, we just have a 5. There's no way you're going to turn that 5 into a 0, so there's no restriction here. So the set builder notation would be x such that x is a real number. So any number for x, because there's no restriction on x. Any questions? Actually, you know what? I'm so used to asking that question. You can't really do that in this format. Sorry about that. All right, so this is the fundamental property of rational numbers, which basically means that you can simplify these fractions, right? So you see this a times c, this b times c, that will simplify to be a over b because, of course, we can cancel out these common factors of c. And the same thing's happening here. You break down this 15 and this 20 so that it's 3 times 5 and 4 times 5. So that way you can cancel out those 5s and you're left with just the 3/4, which is the simplified form of 15 over 20. All right, so our steps here is the first and most important thing is that you need to factor as much as you possibly can with everything that you see. So factor everything before you do anything, and then you're going to apply that fundamental property, which allows you to cancel out the common factors. Okay. All right, so let's just do one of these guys. We'll do this one since it's the most familiar to us, and there isn't much to do with this since you can't, remember, you can't factor a sum of squares. You can only factor a difference of squares, so there's nothing to do here. And we did not talk about the cube functions here. So let's go ahead and factor as much as we can here. So we're going to factor the numerator. So that will be y plus 3 and y minus 1. That's the numerator, and I'm not going to go through the steps on how to factor that. That was chapter 5 material. So hopefully you guys have all studied enough where you are pros at factoring, especially when your a value is 1. And these are pretty small numbers. We should be able to factor those pretty effectively at this point. And then the bottom, so the denominator, so this is going to be y minus 2 and y minus 1, because again, we have a positive product and a negative sum, which means both of our factors have to be negative. Negative 2 times negative 1 is positive 2, and negative 2 times plus negative 1 is going to be negative 3. And then you can see pretty clearly here that you have a common factor of this y minus 1. So we're going to cancel those guys out, and that leaves us with y plus 3 over y minus 2. And one of the most common mistakes that students make when doing these problems is they see these y's here and they fall into the trap of saying, oh, they have a y in common, I'm going to go ahead and cancel those. You can't cancel unless you're multiplying. The reason why we were able to cancel here and cancel here was because we were multiplying this y minus 1 to this y plus 3. We were multiplying this y minus 1 to this y minus 2. Multiplication is the key to being able to use that fundamental property. So if you're not multiplying, which you're not doing that here, then you cannot cancel. So this is your final answer. There isn't anything left to do with that. So this is more of the same. This brings us back to that other idea where things are pretty close, except the signs don't match up. So the moral of the story here is that we just factor out a negative 1. So there's nothing to do with r minus 1. We factor out a negative 1 from this denominator, and that's going to give us positive r and a negative 1. And now we can go ahead, if we wanted to do this, I suppose we could factor out a positive 1 if we wanted to from the numerator, and that will go ahead and cancel those out. And that leaves us with an answer of negative 1. Okay. This one is pretty interesting too. Most students see that this is a difference of squares, but in order to cancel with the numerator here, you've got to factor the negative 1 out first so that the order matches up. See how this is variable first, then number, where you have number first, then variable. You're going to want to factor the negative 1 out from the denominator to get p squared minus 4. And then this is just p minus 2 up top. Now you have a difference of squares down here, which we'll be able to cancel with that. So let's just go ahead and finish this one up. So we've got negative 1, p plus 2, p minus 2, and the p minus 2's will cancel. And that leaves you with negative 1 over p plus 2. And there are other ways to write this answer. You can leave this as 1 over negative 1 times p plus 2. It doesn't matter where that negative 1 goes. So long as it kind of comes along for the ride, you should be good to go. Okay. All right. So quotient of opposites. So again, this is just talking about how you are allowed to factor out a negative 1 if you have pretty much the same stuff that you need, except for the signs that aren't quite matching up. Okay. So to multiply rational expressions, again, the first thing that you're going to want to do, no surprise here, is you're going to factor all the numerators and all the denominators as much as you possibly can, and then see if you have anything in common. So one of the common errors that I see with students with this particular concept is that they start multiplying these polynomials and then they have no way to figure out how to get them back down to size. So you want to factor so that way you can cancel as much as you possibly can. And the little like slogan that I like to use is simplify before you multiply. That is the biggest deal when it comes to these rational expressions and multiplying. Simplify. And the only way to do that is to factor. So you've got to factor first and then go ahead and simplify as much as possible. Apply the fundamental property, which is the whole canceling bit, and then multiply the remaining factors in the numerators and the remaining factors in the denominators. All right, so let's go ahead and tackle this guy. We'll do both of these. So again, you see the c squared plus 2c. We're going to do the fundamental principle, which says there's a c in common. And what I'm going to do is I'm going to just change these to x's just because these c's sort of look like parentheses, and I don't want it to kind of get all muddied up. So I'm just going to change them to x's so you all are aware of that. So we've got x that I'm going to factor out, and that leaves me with an x plus 2 in the numerator here. So this guy is all set. I see that we have a difference of 2 squares in the denominator here. So that will be x plus 2, x minus 2. And then over here, we've got a, so that's all set there. Over here, we've got a quadratic trinomial. So that will factor to be x minus 2, x minus 2. That happen to be a perfect square trinomial. And this guy, again, we're going to use that fundamental principle of factoring, which says they have something in common. They have a, quote, c in common, which we are going to change to an x. So we take out the x, and that leaves you with x minus 1. And now that we have factored everything that we possibly can, we are just going to start canceling out as much as possible, matching as much of the things from the numerator and the denominator as we possibly can. And you can see that you end up with a pretty clean answer of x minus 2 over x minus 1. And again, don't go canceling those x's out. The only way that you can cancel is if you're multiplying. This is x minus 2. This is x minus 1. No longer multiplying, so you should not be canceling. That is your final answer. Okay, so let's go ahead and take a look at this one. So this will be m plus 4 and m minus 4, because that is a difference of 2 squares. This is going to be m plus 2 times 1 over m plus 4. So this time there wasn't a whole lot that we could cancel, but we've got something. So we've got this m plus 4, cancels with that m plus 4, and we're left with just this lonely m minus 4 over this m plus 2, and we're done. Okay. All right, so finding the reciprocal. So most of you guys probably remember this from taking courses before you started taking this one. Reciprocal is the fraction that is flipped, and you need to do this idea when you are dividing fractions, because you cannot divide fractions. So what we do is we multiply by the reciprocal. Some of you might remember the term like keep, change, flip, as teachers like to use that to remind their students that that is how they're supposed to, quote, divide fractions, is that you keep the first fraction the same, you change it to multiplication, and then you flip the second fraction. So that's what we're going to do when we're dividing fractions. Okay. So we'll go ahead and bang this one out. So again, we're asked to divide these fractions, which we can't do. So we're going to keep the first fraction exactly as it is. We'll factor it if we can, which there really isn't much to do with this first fraction. I'm going to change this to multiplication, and then I'm going to flip the second fraction. So this is going to be a 5 in the numerator, and there is something to factor out from this now denominator. So I might as well get some bang for my buck here and factor out what I can while I'm at it. So there's a 3 in common, which leaves you with 3 and then parentheses 5p plus 2, which is beautiful for us because we have a 5p plus 2 over here and a 5p plus 2 down there. So we're just going to knock those right out, and that leaves us with a final answer of 5 over 18. And we're done with that one. All right, so let's go ahead and do this one. This one's a little bit more complicated, a little bit more work to do, but we should be able to do this one with a little struggle as well. So again, we're going to keep, change, and then flip. But as I'm keeping and I'm rewriting, I might as well factor because we know that we need to factor as much as we possibly can as well. So this has a q and then a q plus 2 because there's a q in common. And then we've got this 5 plus q over there. I'm going to change it to multiplication, and then I'm going to flip the second fraction. There's a 3 in common, which I will factor out, which gives me a q minus 2. Okay, and then this is going to be over that. And once again, these guys aren't quite matching up the way that I would like them to match up because the variable is after the number. So I'm going to factor the -1 out first, and then I will have a difference of 2 squares of q minus 2 and q plus 2. And this is great because we can now cancel those out. We can cancel those out. And that's going to leave us with just 3q in the numerator and this -1, 5 plus q. And this is a good time for me to just mention to you, you are going to be able to leave your answers in factored form. If this were actually, I should go back because this is now MATLAB that's going to be assessing you, no longer me. So in MATLAB, it's probably not going to accept this answer. If this were a test that I was grading, I would encourage you to leave this as your answer. But unfortunately, a computer is going to be kind of taking over my job as far as grading for the rest of the semester. So they're probably going to have you distribute that negative in to get some answer that looks more like this. Okay. So now that we're officially done for the rest of the semester as far as our in-person meetings, MATLAB is going to be your mode of assessment going forward. So if you haven't registered for MATLAB, please let me know if you need assistance, because if you don't register for MATLAB, you can't do any of the tests going forward or the final exam. So just reach out to me so that we can get you situated and get you on board with the rest of the tests and the homework, obviously. All right, so that's it for 6.1. So now we're on to 6.2, and we're getting pretty close to being done with this first video. I don't want these videos to be super long so that you're sitting there spending up all of your time watching them. Plus, I'm sure that they're not very interesting. So let's go ahead and just quickly talk about 6.2, and then I'll create another video for the remainder of 6.2 and 6.3. Okay? All right, so adding and subtracting rational expressions. So if the denominators are the same, then we add and subtract the numerators. Pretty nice. So this is the sunshine and rainbow situation when it comes to fractions, when you're adding and subtracting. When the denominators are the same, we're good to go. We just add or subtract the numerators depending on whether we're adding or subtracting the fractions. So again, sunshine and rainbows. You need to have the same denominators in order to add and subtract fractions. So that's where the challenge is going to happen when we don't have it. So for now, when the denominators are the same, we just go ahead and do what we need to do. It shouldn't be too challenging for us, okay? If the denominators are different, then we need to find the LCD of those denominators so that way we can go ahead and do what we got to do. And then we'll simplify and write our answers in lowest terms. So again, our sunshine and rainbow situation, we have a 9 here and a 9 there. We have exactly what we need. So all we have to do is add the numerators, which there isn't much to do because they're not common terms, right? They're not like terms. And then remember, the denominator stays the same. It will not change. The reason why we could add these in the first place was because these were the same. So it's going to stay the same. The only way that this guy's going to change is if it can cancel with something in the numerator. And again, that has to be a common factor. It's got to be multiplying in order to be able to cancel with something down here. All right. Once again, we have this 3x to the third and a 3x to the third. It's the same. So we are going to keep it the same, 3x to the third. And then we have this 8 minus 14, which will leave us with -6. Okay. So now we've got a situation where we actually can simplify. So we've got -6, and then we've got this 3. So we should be able to simplify that so that it is -2 over x to the third power. All right, we canceled out the common factor of 3. Alrighty. So again, sunshine and rainbows, when the denominators are the same, we just add or subtract the numerators like they tell us to do. Okay, so same thing is happening here. Denominators are the same. We get r plus t, and then this r squared minus t squared. And if you're not careful, you may think that this is all you need to do for this problem, except you should hopefully have noticed that this denominator is a difference of two squareds. So this really should be r plus t over r plus t, r minus t, and then you can see immediately that the r plus t's will cancel out, leaves you with just a 1 in the numerator and then an r minus t in the denominator. So this one definitely has a little bit more to it than just adding and subtracting, because you had to factor the denominator to see if you can cancel. Okay. And then over here, we're going to do something similar again. So this is going to be x plus 6, because we do have the same denominators already. And you might as well try to write this denominator in factored form right now to see if it will cancel. So you've got this negative 18, and you've got this 3 here. So does that factor to be a factor of x plus 6? I'm not sure. Let's think about it. So what are my factors of negative 18 that add up to 3? Let's see here. So factors of negative 18, definitely not negative 1 and 18. Definitely not negative 2 and 9. The ones that I can kind of jumping off my head are 6 and 3, and that's actually the winner, right? So we've got x plus 6 and x minus 3. So again, if you're someone who's not 100% confident in factoring, that's kind of how you need to work these things out, is you just think of the factors of the 18 or whatever this number is that will add up to the number in the middle, okay? And we'll go ahead and knock those out, and we have 1 over x minus 3. We're done. All right, so finding the LCD. This is where all the magic happens. So finding the LCD is we're going to factor the denominator as much as possible, okay? We're going to find the least common denominator as the product of all the different factors from each denominator, with each factor raised to the greatest power that it occurs in any denominator. So the largest number of times that it shows up is going to be part of the LCD, okay? So when you look at the LCD of these groups of potential denominators, now they're not actually in denominators, we're just kind of telling you that they are. So you look at these and you say, all right, we have 10 and we have 15. What would be the LCD if we just had 10 and 15? And most of you guys will know that the LCD between 10 and 15 is going to be 30. And then remember, it says that the highest exponent, right, the largest exponent is going to be part of the LCD. So we have a to the third power, and we have a squared. So a to the third power is obviously more than a squared. So a to the third power is going to be part of the LCD. Over here, you have b to the fifth and b to the sixth. Again, b to the sixth is showing up more times than b to the fifth. So b to the sixth is going to be the LCD. And that is it. That's your entire LCD. Now the challenge, and this is going to happen in the next video, is this is the LCD. The challenge for us is going to be turning this denominator into that, and turning this denominator into that. Because it's not enough to just know what the LCD is. You have to be able to create it. And that's going to be, again, our challenge for the next video. That's how we'll start that next one. We're just going to kind of get used to finding the LCD right now, and then we'll go ahead and actually create it in the next video. So over here we have the Z, and this is, I think, a pretty good strategy. I'll show you what I usually do for these is I kind of write each one, and I say, all right, this is Z, and this is Z plus 6. And I start writing this in factored form. Well, Z in factored form is pretty dull. It's just Z. And Z plus 6 in factored form is just Z plus 6. Again, there's really not a whole lot going on. And when you look back at the definition of the LCD, it says it is the product of all the different factors from each denominator, with each factor raised to the greatest power. So we don't really have to worry too much about the power business here because there's nothing that's showing up more than once. So it's the product, meaning multiplication of each individual factor. So our LCD is going to be Z parentheses Z plus 6. Okay. All right, let's see if we can find one that's a little bit more interesting now. Here we go. So again, I'm going to start off by writing off to the side m squared minus 16, and then I have this m squared plus 8m plus 16, and I'm going to write them in their factored form. So this is, of course, the difference of squares, so m plus 4, m minus 4. This one looks like a perfect square trinomial, so this is going to be m plus 4, m plus 4, or m plus 4 squared. So you can see by that definition that it is the greatest exponent, right? The greatest power. So this m plus 4 to the first power, this is m plus 4 to the second power. So this is going to be part of the LCD where this is not. So my LCD for this first one is going to be m plus 4, m plus 4, and m minus 4. That's how I would write that. I think it's in your best interest to write it in expanded form, not in exponential form, just so you can see the clearest picture of what's actually happening here. All right, and we'll do this last one for tonight, and we will call it a video. So again, we're going to write each one of these. So x squared minus 2x plus 1. We have, hitting the button here, x squared minus 4x plus 3. And then we have 4x minus 4. So we're going to write all of these in factored form. I'm going to start with this one since it's the easiest one. They have a 4 in common. Factor it out. You get an x minus 1. Over here, this is going to be x minus 1, x minus 1. That's a perfect square trinomial. And this one is going to be x minus 3 and x minus 1. So of course, when it comes to the LCD, it is the product of each individual factor raised to the highest power. This is going to be x minus 1 squared, so that guy is going to be part of the LCD. Of course, this 4 is going to be part of the LCD, so it'll be 4, x minus 1, another x minus 1, and then this last but not least guy over here, x minus 3. And that is it for tonight. So I hope that this was helpful in getting you through some of the notes. Let me know if there's something else that I can do for you. But in the meantime, take a look at this. I'm going to post the video, and I will do a collaborate video with you guys on Friday, so that way you can ask questions, get some feedback from me. I can get some feedback from you guys, and hopefully we can make the best of this whole situation. Okay. Let me see.